Hello and welcome to Lecture 11 for ECE 108. Last lecture we ended with the question of when can we find the inverse of a function, or when can we undo a function. So in this lecture we're going to quantify that by introducing some properties that functions may or may not have. So we'll start with injective functions. So a function f mapping from x to y is injective provided that for all values x1 and x2 and x, so any two values in the domain, if f of x1 is equal to f of x2, then x1 is equal to x2. So some more terminology. Injective functions are often called one-to-one functions or injections. So fancy definition, bro. What does it really mean? Well, let's try to unpack this a little bit. For any given y in the set y, there is at most one x in x such that f of x is equal to y. There may be 0 values of x that map to that value of y, but there is at most one. So explicitly, this important note here, there may not be a value of x in x that maps to any given value y in y. So graphically, let's bring back our friend the function from last lecture. So the function from the previous lecture, here I have the domain x, I have the codomain y, and I have the range of the function f of x. So this function is not injective. Why? Because for this value of y3, I have 3 values in the set x that map to it. So if I wanted to make this function into an injective function, I would have to restrict the domain of the function to delete at least 2 of these points. So in particular, I could delete the points x5 and x4, and now my function is one-to-one because for each value in y, I have at most one value of x that maps to it. So this is the idea of injectivity in a nutshell. So the next kind of question that might come up is, how do I prove something's injective, or how do I disprove that something is injective? Well, we have a slide for that. To prove that a function f mapping from x into y is injective, we first have to assume that f of x1 is equal to f of x2 for some x1 and x2 in x. So here I'm assuming that I have one value of y, and that gets mapped to by 2 values in x. Next, I need to conclude that if this is indeed the case, then x1 has to equal x2. So in other words, if I prove that this holds, I am proving that if f maps something to some value y, and f maps something else to that exact same value of y, then the two things that f was mapping to the point y are the same thing. So let's give an example of this. Prove that f mapping from the positive real numbers to r defined by this x is equal to x squared is injective. To do this, I first assume that x1 squared is equal to x2 squared. Why? Because x squared is my function. And I'll assume that this holds for some positive real numbers x1 and x2. So next, from here, I need to conclude that x1 is equal to x2. So how do I do that? Well, let's solve this for x1. So if I take the square root of both sides, that gives me x1 is equal to plus or minus x2, right? When I take the square root, I get those 2 roots. So at this point, it looks like I could have 2 different values. I could have a positive value and a negative value. Well, since x1 and x2 are both greater than 0, I can't have the case where x1 is equal to negative x2. Thus, x1 has to be equal to x2, and therefore f is injective. So this is the general process that you'll use to show injectivity. So next, how do I disprove injectivity? So to prove that the function f from x to y is not injective, we need to find an x1 and x2 in x such that x1 is not equal to x2 and f of x1 is equal to f of x2. So essentially we need to find a counterexample. So prove that the function mapping from the real numbers to the real numbers defined by this quadratic mapping is not injective. Well, we note plus and minus 1 are both real numbers, and negative 1 squared is equal to 1 squared, but negative 1 is not equal to 1, thus f can't be injective. So a key concept to get out of these 2 slides is that simply by changing my domain, I can change a function from being injective to not injective. And in fact, we saw that on the first slide where I introduced the concept of injectivity. I can always restrict my domain to make a non-injective function injective. So now let's look at one more type of function, surjective function. A function f mapping from x to y is surjective if for every y and y, so instead of talking about the domain, I'm now talking about the codomain, if for every y and y, there exists an x and x such that f of x is equal to y. So alternatively, f is surjective if the range of f is equal to y. Well, why does this work as a definition? Well, if for any y and y, there's something in x that f maps to it, by definition, every element of y is in the range of f. So finally, surjective functions are also called onto or surjections. Okay, now we have a definition that might look a little bit complex, so what does it really mean again? Well, for any y and y, any number or value or object in y that I can give you, there is at least one object in the set x such that f of x is equal to y. There could be more than one, but there's at least one. So again, important note, there need not be a unique x for every value of y, or explicitly, there can be lots of values of x that map to y. So graphically, let's pick our function from earlier. So this function is not surjective. Why? Well, take a minute and think about it. Okay, so this y4 and y5 don't have associated values of x. So what could I do to this function to modify it to make it surjective? Well, I can leave the domain the same this time, and I can restrict the codomain. This y4 and y5 are points that didn't have any x value that mapped to it. Therefore, if I throw them away, I can become surjective. So in this case, I have y1's mapped to by x2, y2's mapped by x3, and y3 is mapped by these three values. So this function here is surjective, but notice it's not injective because this x3 through x5 all map to the single element y3. Okay, so that's all fair and good, but now how do I prove something surjective, or how do I disprove that something is not surjective? Well, to prove that something is surjective, I need to first let y and y be given, so pick some arbitrary element in the codomain, and then I need to show that there exists an x and x such that f of x is equal to y. Equivalently, but less usefully in a lot of cases, you can simply show that the range as a set is equal to the codomain. Sometimes that can be useful, but more often than not, it's not the easiest way to approach a problem. Okay, so let's give an example of this. So prove that the function f mapping from R to R plus defined by this quadratic mapping is surjective. Again, this function is indeed a function because for any given value of x, there's only one value that I'm mapping that value of x to. So how do I show that this is surjective? Well, first, let some y in the codomain, so in this case, the non-negative real numbers, be given, and consider the equation y is equal to x squared. So now from here, I want to show that there's a y such that f of x is equal to y. So I really need to find the x given the value of y. How do I do this? Well, I have to solve this expression for x. In general, you can't do that analytically, but for this case, we can. So taking the square root of this, I find that x is equal to plus or minus the square root of y. Now, the next thing I need to do is to guarantee that these values of x are in the domain of my function. Well, to do that, I need to know some information about y. In particular, if y was a negative number, then x would be imaginary, so this would not be a surjective function. Well, since y is greater than 0, I know x is going to be a real number. Therefore, f is surjective in this case. So now how do I disprove surjectivity? To disprove that a function f from x to y is surjective, I need to find a y in y such that f of x is equal to y is not satisfied for any value of x. So explicitly, this is finding a counterexample. So let's look at an example. Prove that the function f mapping from z to z, defined by f is equal to this linear mapping here, is not surjective. Well, as usual, when trying to find a counterexample, it's usually best to start by just examining the object that I want to find a counterexample for. So let's do this. So consider the equation y is equal to 5x plus 3. So if I want to show that this is not surjective, I need to show that there's some value of y such that I can find no integer x that would satisfy this equation. So let's, again, solve this for x and see what happens. Solving for x, I get y minus 3 over 5. So now, if I want to show that this is not surjective, I need to show that this thing is not an integer for some value of y. Well, that's true for a lot of integer values of y. So in particular, I could pick y is equal to 0. So in the case where y is equal to 0, the only value of x that satisfies this equation is negative 3/5. So if you want to be super formal, you'd want to argue why there's a unique solution to this equation, but we're just taking that as a given for this course. So for this value of y, the only solution is this value of x. That value of x is not an integer. Therefore, f cannot be surjective. So now, as an exercise, use the rough work above to formally prove by contradiction that f is not surjective. So it's not technically incorrect to say, well, if y is equal to 0, the only solution to this is this value of x, which isn't an integer, therefore you're done. But this is a good exercise where you could practice your proof by contradiction. So thinking about it a bit, what would we contradict? Well, we could say let y equal 0, and we could assume that there is an integer solution to this equation, and then get a contradiction from there. So kind of outlined the formal proof a little bit, but that would be a good exercise. So now we have surjective functions, we have injective functions. Are there functions that are both? Well, yes. So prove that f mapping from R to R defined by this linear mapping is both injective and surjective. So do recall that previously we showed that this function, if I was mapping from the integers to the integers, was not surjective. So do keep that in mind, that again, picking your domain and codomain can change whether or not a function is injective or surjective. Okay, so to show that f is injective, we first assume that f of x1 is equal to f of x2 for two values x1 and x2 in R. So we now need to conclude that x1 is equal to x2. So to do this, we simply solve this for x1. So solving this for x1 gives me that x1 is equal to x2. In your work, you might want to say like subtracting 3 dividing by 5 gives me this. But either way, we get x1 is equal to x2, therefore f is injective. Now to show that it's surjective, we need to let y be an arbitrary element of the codomain, so in this case R, be given, and we need to consider the equation y is equal to 5x plus 3. So we need to show that this equation has a solution for x. So how can we do that? Well, we can solve this equation. Solving for x gives that x is equal to y minus 3 all over 5. So from here, x is going to be a real number for any real number y that I plug into here. So since my domain is now the real numbers, this is now going to be surjective. So since this function is both injective and surjective, we give it a name, we call it bijective. So now, definition of bijective functions. Well, okay, technically that works, right? We have an injective, we have a surjective, we now have a bijection. But let's be a little bit more formal than PPAP here. Okay, so jokes aside, a bijective function is a function that is both injective and surjective. Okay, so graphically, bijective functions look like this. So for any given x in my domain, there is at most one value y in the codomain that it gets mapped to. And for every value y in my codomain, there is at least one value x in my domain that maps to it. So if you put these two together, I get that the domain and the codomain have the same number of things, and we have this nice mapping that kind of looks like this. So to prove that a function is bijective, we prove it's injective and prove it's surjective. So we've given plenty of examples of doing proofs for both injectivity and surjectivity, and we gave an example for proving bijectivity already, so we're not going to cover any more examples here. One more thing before I go on, if I wanted to show that a function's not bijective, I need to show that it's either not injective or not surjective. Once you prove that one is not true, then you're done. Okay, so now we've done all of this work, and I promised talking about inverse functions, or undoing a function, and so far I've done none of that. Let's talk about inverses. For injective functions, we can define an inverse. Why? Well, if I go back to my classical picture of an injective function, for any given injective function, each element in the codomain of the function is mapped to by at most one value in the domain. Therefore, I can undo what f does. basically for y1, I have a unique value x1 that I can map to. For y2, I can uniquely map it to something in the domain. Same thing for y3. These values y4 and y5 don't have anything to map to. Because of that, I'm ultimately going to restrict my domain in a second. Note that we can't do this for functions that are not injective. For instance here, for this value of y3, what am I going to map it to? I can't map it to 3 different values for it to still be a function, because a function has a unique value for any given input. And this would not be true for non-injective functions. Okay, so let's give a definition. For an injective function f mapping from x to y, the inverse of f, denoted by f inverse, is the function f that maps the range of f into x, and that will be given by this function here. I take some value of f of x, and I map it to x. So note, using this notation with the f of x here instead of x might look a little bit awkward, but the elements of the range of f are elements of the form f of x, so this is indeed proper notation here. So graphically, let's look at this again. So here, my range of f is simply going to be this collection here in red. So now if I restrict my domain of f inverse of f to be the range of f instead of all of the codomain of f, f inverse becomes a function. So explicitly, if I try to define f inverse from y to x, it would not work because y4 and y5 don't map to anything, and that violates the definition of a function. So now, that's the basic idea of inverses. Let's talk about some theorems involving inverses. So, if f is a function that maps from x to y, and in particular f is a bijection, then so are f inverse and f inverse inverse, and f inverse inverse is equal to f. So the proof for this is in the book under claim 20, so I'm not going to go through it in detail because you can just read it. But let's briefly talk about the things that you have to prove to show this. So first, we're going to assume f is a bijection. And since we're now talking about f inverse, we need to A1, show that f inverse is a function, and B, show that as a function, f inverse is both injective and surjective. So that is what needs to be shown to show that f inverse is a bijection, and that's done in the text. And next, to show that this f inverse inverse is a bijection, I first need to show that f inverse inverse is a function, and then I need to show that it's both injective and surjective. And finally, I need to show that f inverse inverse is equal to f, and like I said, the proof for that is outlined in the text, so I will refer you to the text for the formal proof. If you have any questions, you can of course ask on Piazza or in office hours, so just keep that in mind. So next, claim 21. If f is a function that maps from x to y, and this is an injection, then f inverse mapping from the range of f to x is a bijection. So what do I need to do here? First, I need to show that f inverse mapping from the range of f to x would be a function. And secondly, I need to show that it's both injective and surjective. So the main issue here is that this initial function f that I started with is an injection, but it might not be a bijection because we don't know if it's a surjection or not. And this is really where this restriction of f inverse from the range of f will come in. Because I know if I have any given function, if I restrict its codomain to be the range, by definition, it's surjective. So that's the main thing I need to overcome to prove claim 21. So again, the proof is in the book, but if you have any questions, you can ask in office hours or on Piazza. So next, claim 22. There exists an injection f mapping from x to y, if and only if there exists a surjection g mapping from y to x. So just kind of unpacking the basic idea here, if f is an injection, then that means that for any given y in the codomain, there is at most one value of x and x that gets mapped to it. And if g is a surjection, for any given x and x, there is at least one value of y and y that maps to x. So thus, one could expect that the existence of a injection from x and y is equivalent to the existence of a surjective function from y to x. This is kind of a hand-wavy intuitive argument, which means that that argument's not sufficient for proving this claim, but that's the general idea of why you might expect it to be true. To actually prove this claim, you need to use the power set, and that is done in the text on page 45, which I highly suggest you read. If you have any questions, you can ask in office hours or on Piazza. And I'd like to reiterate, if you have any questions on any of these claims or the proofs, office hours is probably the best place to ask, but I can, of course, address them on Piazza. It's just text isn't necessarily the best media. Okay, so now we have functions, we have injections, surjections, and bijections, and we have inverses. The next natural thing that we can talk about is composition of functions, and then we can ask questions about the composition of injective functions, surjective functions, bijective functions, mix and matching them. So that's what we'll start talking about next week before we get into the idea of cardinality and the concept of infinity and how to count infinity. Okay, so read pages 43 through 45 with the focus on the proofs of claims 20 through 22. I highly suggest you read the proofs of these claims to the point where you understand what they're saying and what they're doing and a bit of why they're doing it. So do feel free to ask questions on that in office hours or Piazza. And now, just a reminder, when you feel a little down, make sure you take some time for self-care like Hot Doggo here. Finally, I'd like to announce that we now have a sponsor. This video is sponsored by the University of Waterloo. If you would like to see more content like this, like, subscribe, and keep paying your tuition. Mostly the last one, though. Have a wonderful weekend, and I'll see you all next week.